Yeah, thank you. All right, then thank you, Professor Tellex, for coming. You agreed to do a 60-minute keynote, which is really awesome. So Stefanie is an associate professor in the computer science department at Brown University. The aim of her research program is to construct robots that seamlessly use natural language to communicate with humans. Robots that can communicate with people using language can respond appropriately to commands given by humans, ask questions when they are confused, and request help when they get stuck. Her work applies probabilistic methods, corpus-based training, and decision theory to develop interactive robotic systems that can understand and generate natural language. She was named one of IEEE's Spectrum AI's 10 to watch and won the Richard B. Salomon Faculty Research Award at Brown University. Thanks, Stefanie, and you can get started with your presentation.
Super. So we're a relatively small group, so please feel free to interrupt me if you have questions. I think that the way that you would do that is raise your hands, and the organizers will then tell me that that's happening. But there's a little bit of a higher barrier to doing that when we're in this weird Zoom situation. So, you know, I want to try to like encourage you extra to like, you know, overcome that barrier. And if you want to ask a question, please do go ahead and raise your hand. And I'd be happy to take it, and we can sort of have a discussion. So this talk is called Teleoperating Mobile Manipulators in Virtual Reality. So I think that robotics is a tremendously exciting field right now because we are seeing our robots move out of the research environment and into the real world. So when I was a postdoc at MIT, I worked on this robotic forklift project that was led by Professor Seth Teller to make an autonomous vehicle that could drive around in warehouse environments. Now we have Waymo cars driving around in the streets of Mountain View and in other places too, you know, doing autonomous driving, and there's this potential for these vehicles to really make a tremendous impact on every aspect of our society. At Brown, I teach a class about autonomous drones where each student gets their own Raspberry Pi Python drones. This platform costs $225 in parts, and all the autonomy is onboard implemented in the Python programming language, which makes it really accessible for teaching because you don't need to make people install ROS and you don't need to make them learn C++. And they can do real autonomous robots. And this is a shot from our class. We're going to be teaching it. I'm teaching it this fall fully remotely. So this shot won't be possible this fall, but we're still distributing lots of drones to students. And there is a commercial company called Skydio that has created, they just released their second version of the Skydio autonomous drone. And the platform, well, the first version anyway, had 13 cameras, stereo pairs for each of the 6 sides of the cube, as well as a high resolution color camera. And it was capable of fully autonomously following a person through the forest, avoiding the trees and other obstacles as they were doing like crazy things like mountain biking and recording you with the camera, with no human pilot, completely autonomously. So there's been a tremendous amount of advance in robotics over the past 10 years in autonomy and in their capability. And that makes us have to answer this question of how are we going to tell the robots what to do? So this is a shot of my son when he was a baby with the PR2 mobile manipulator robot. So this is a robot that was created by a company called Willow Garage, and they made about 50 of these robots. They gave 10 of them away to universities like Berkeley and MIT, and they sold the others, and they were distributed around the world, mostly to universities. And lots of people use these robots to do lots of things. And the idea was to advance a stream of robots being in the home. So the question in a lot of my research is kind of how, if we have these robots in our homes and in every aspect of our life, how are we going to tell them what to do? And the state-of-the-art answer to that today is two-dimensional interfaces, usually on a touch screen of some kind. So this is an example of that from the forklift project. They had a touch screen interface where you could circle the pallet that you wanted the robot to pick up, and then you could circle where you wanted it to go, and it would go and do it. And even today, if you get in one of the Waymo cars, there's a screen on the back of one of the seats, and that's where you can tell the car what to do, and also you can see what it sees. You see the pedestrians and stuff like that it's detecting. So a large part of my research program is about, as Tom was saying, making the robots use language, understanding natural language, in order to have us tell them what to do. But one day, I guess it was probably 6 or 7 years ago, my students were like, hey, this VR stuff is really cool. And I was like, we do language, I don't do VR. And they were like, but it's so cool. And I was like, we do language, I don't do VR. And then they borrowed a VR system from somebody, and they set it up in the lab without telling me. And I walked into the lab, because in those days you could walk into your lab, like you can't do that now, but in those days you could. And I put, it was an HTC Vive, this kind with the lighthouses, and I put it on, and I was like, I was just completely blown away by how good it was and by how cheap it was. It was totally amazing. And then I was like, okay, we're buying VR now. And so we started doing VR after that. So I'm going to tell you about this sort of thread of work that we've been doing since that time in virtual reality and augmented reality. We later on got an augmented reality headset, the Microsoft Hololens, to kind of explore these interfaces. And one of the things that motivated us is this video. So this is a video from 2011. It is of a robot called the PR1, which was a predecessor to the PR2 robot that I was just telling you about. So this was created by Andrew Ng's lab at Stanford. And what they were interested in doing is creating robots that could operate in the home. And they made this new mobile manipulator hardware platform, the PR1. I'll play it again so you can kind of see it. And this was then picked up by Willow Garage and turned into the PR2. And this was the video that they were showing everybody when they were trying to explain what their vision was that we want robots in the home. We want robots cleaning up your house. We want robots doing tasks that humans don't want to do. We want them to do those tasks autonomously without human intervention. So here in the scene, there are no people, right? But this video is actually created through teleoperation. So, and they told us this wasn't like a secret. Their goal was to say, here's this hardware platform, and here's what it's capable of when teleoperated, when controlled by a person. And now we're going to distribute 50 PR2s. And we're going to go and we're going to make these and the community is going to go make autonomous algorithms to make the PR2s do stuff like this. And then a really interesting thing happened in the next 10 years, which is that, as far as I know, and I would love for people to find counterexamples of this, but as far as I know, there is no PR2 video that I'm aware of, teleoperated or autonomous, that does anything like what this video is doing here. And again, this was teleoperated. And that, to me, is a real mystery, because this is like, whoa, this is cool. Look at how he's straightening the magazines and like picking up things and straightening to pick up the magazine, he's got to slide it off the table and then, grab it from the side and stuff like that. There's really a lot of very dexterous manipulation. And in these deep, dark days with deep learning, we would love not only the ability to teleoperate like this, but we would also love the ability to collect data of this sort, of the robot doing lots and lots of complicated autonomous things. Even if we had to teleoperate to do it, because then we could train from this data. We could learn autonomous algorithms to do it. So how was this video created, right? They sent out 50 PR2s, but as I said, I've never seen a PR2 do this, even teleoperated. So how is this video created? So to find out, we actually had to do a little bit of like old-fashioned research. One of my postdocs, Lawson Wong, was at Stanford at the time that this was being done. He was an undergraduate there. And he was visiting Andrew Ng's lab because Andrew Ng's lab was a cool place to visit. They had all kinds of robots. And here you see a robot that is emptying a dishwasher. It's got lights shining down on it. It's a mobile base. It's emptying the dishwasher. So he took a bunch of pictures while he was there in the lab. So what we're going to do is like an old-fashioned video editing technique. We're going to crop, and then we're going to zoom and enhance. And we're going to look at the background of this image that Lawson took. And what you see in the background, not in the shot, because this wasn't as cool as the autonomous robots, is a gantry system. So this is the gantry system that they used to control the PR1 robot to make that video. So the way that it worked is that you put your hands in those blue things, and it had those, I forget what they're called. Somebody tell me what they're called. Those pens that can give you the 3D feedback, like force feedback. You remember what those pens are called? Somebody? You can like feel, it's like this tactile feedback thing. It's haptics, right? So you can feel stuff. The robot can kind of push back on you through the gantry system. And you can move your hands in the full 6 degrees of freedom that your hands have, right? X, Y, Z, roll, pitch, and yaw. Rather than trying to use, specify a 6 degree of freedom pose for the robot's hand, with the 2 degrees of freedom you get from a mouse or a touchpad, you get the whole 6 degrees of freedom. So we did some more digging, and Lawson just remembered this when I was like, how did they make this video? What happened? And he went and grabbed these pictures. And we went and looked. This was briefly referenced in the ICRA paper about the PR1. Robot software supports teleoperation control. That's what they're called, Sensible Technologies Phantom 3.0 input devices, and a foot pedal arrangement. So those sensible things were these off-the-shelf haptic devices, so that if the robot hits the table, you feel that. You can't push down, and it pushes back on you. And then we think, we're not sure, but we think the person uses their own eyes to survey the scene. So they're off camera, but they're looking at the scene with their eyes. And they're using this intuitive mapping they have with the gantry system in order to control and in order to make this video. So this is, in my opinion, why the PR2, despite being sent to all of these universities with all these brilliant people, why the video demonstration we saw of the PR1 was really never reproduced. It's because they had this fancy gantry, and that fancy gantry was expensive, and it was mechanical, and it was specific, and it was hard to clone in other places. The teleoperation interface that came with the PR2 was a PlayStation controller or a keyboard and mouse interface that they used through ARVIS. So we, in my lab, had got this HTC Vive system, and obviously the thing that we were going to do was put our robots in virtual reality. And the sort of inspiration that we had, and to us, it was really interesting to me about this whole project was like, for us, using, we didn't even call it a virtual gantry, but like, but we made essentially a virtual gantry system in VR, and it seemed to us to be like the only obvious interface you could do. We realized later that it really wasn't, that there's lots and lots of different interface concepts. And co-published at around the same time of our interface, the virtual gantry, Daniela Roos created an interface that is inspired by Inside Out. If you've ever seen that Pixar movie, where you're like the homunculus inside the brain, and you're looking out through the robot's eyes. The PR2 actually had a VR interface. This also was never published, but it was demoed, and there were videos. And in those interfaces, you put the headset on, and it was like you were looking out of the camera. If you moved your head, the camera, what you saw moved also, exactly. So it was like when the VR system loses tracking, and it displays that message, and it's always floating right in front of your head. Rather than being able to walk around in the scene. But what we created was this system where we put the robot in the scene, and then we calibrated all the robot sensors. So we had a Connect 2 depth camera, and we knew the depth camera's pose relative to the robot. And then we made it so that you could be in the scene and look at the robot's body and look at the sensor data. And you could move the virtual body around using the full 6 degrees of freedom of your hand in order to command the robot to do different actions. And this is in contrast to the keyboard and mouse interfaces. So here's an example of the RViz interface that kind of came with ROS, where you had this 2D interface and you can see how they're putting these like dragging arrows and stuff to turn the arms around and drag them up and down. And then like physical gantry interfaces. So a very famous robot is the Davinci Robot here on the left. This is the surgical robot that goes and does surgery. And the surgeon operates in this essentially gantry kind of system where they're controlling physical grippers in one side of the room, and the robot is translating that into motions inside the patient when they're doing the surgery. Okay. So I'll show you a video of kind of what this looks like.
Here at the Humans to Robots Lab, we are working on virtual reality teleoperation interfaces for robotic control over long distances. This is a Baxter robot at the Massachusetts Institute of Technology in Cambridge, Massachusetts. 41 miles away at Brown University, Eric here is going to control the robot using a VR headset and hand controller. In the VR scene, Eric is able to see a point cloud generated from Connect 2, the wrist camera of the robot, and a 3D model generated from the robot's URDF. As Eric changes the hand controller's position and orientation, the end effector's position and orientation follow accordingly. Here, Eric is completing the YCB cup stacking task, stacking 10 cups from the YCB object database. Note that our system allows for teleoperation over long distances because all data is sent over the internet, allowing the teleoperator and the teleoperated robot to be in any two locations with an internet connection. Now, we will watch Eric stack 10 cups in a row, sped up at a rate of 8 times.
So this gives you a sense of what the interface was like, and we're being lame, I know. So like James, our collaborator James Tompkin, is always telling us that we're just like, the easy thing to do was to just take the points from the point cloud and throw them in space, so you see this kind of speckled thing. But there's a mesh, there's like standard mesh things, and we know we're supposed to do them and we haven't done them yet. And I'll talk about later what we're going to do like to make that better. And actually that mesh that you're seeing in the, I'll go back so you can see a still of it. That mesh that you're seeing is a major limitation, or the lack of a mesh rather. You basically drop resolution as you get farther from the camera because the points are kind of spread farther apart. And that makes it pretty hard to see like fine details of what's going on in the system. But that said, especially an expert user who's used to this, you're able to do pretty fine-grained and dexterous tasks with the robot. And we wanted to see how this worked, so we also did a user study on this cup stacking task. To make it harder, we actually tilted the cup, because many of the 2D interfaces, like if you're only using this crane, like where you're moving X and Y and then going down, it kind of makes it easier for the keyboard and mouse interface. But when you have to insert something in at an angle, you really need the full 6 degrees of freedom of the arm. So the idea was to teleoperate the robot and do this cup stacking task. And we compared it to a bunch of different baselines. So to upper bound how well you could do, we did direct manipulation. So that's where you grab the arm, the robot arm, you put it in zero gravity mode, and you physically grab the arm and move it around to do the task. So you don't touch the object yourself, but you get to use your hands to move the arm directly, and you get to use your eyes, and you can put your eyes wherever you want in order to see what is happening. So this is never going to be, we're never going to be able to beat this, but it provides a measure of both whether it's physically possible to do this task with the robot and how far we are from like this theoretical upper bound of how good we could do. Then we tried a keyboard and mouse task. So we made an interface that was inspired by RViz and Gazebo and ROS, but we made it with Unity, which is the VR. I guess you all know this is the VR system that many people, but not all people use. Then we tried the monitor interface where you're seeing what's going on in 2D with a monitor, but we're using the VR hand controllers to move the robot. So the idea was to try to separate out whether it was having 6 degrees of freedom control that helped or having 6 degrees of freedom control and having the perception helped. So in the positional hand tracking mode, you just get to move the robot with the hand controllers, but you're looking at a monitor to see where everything is and what the sensor data is showing. And then finally, our last condition was full-on VR with the HTC Vive, where you use the hand controllers and the VR headset so that you can move your head around and see everything as if you're standing next to the robot. And what we find, and we always measure, I always like to measure in all of our studies, both objective measurements, so like in this case, how long does it take to complete the cup stacking task in seconds, and also subjective measures. So how much do they like it? How much do they rate the workload? So here on the, can you see my mouse? I don't know if you can see my mouse. I hope you can.
Yep.
Yeah.
Yes, sweet. Okay, so here the mean is showing the time to complete the task in seconds. So if you're using direct manipulation, you can do it in about 8 seconds. It takes like 2 minutes with keyboard and mouse. It takes just over a minute if you're using the hand controllers with the 2D perception interface, and it takes just under a minute if you're using the full-on VR. And you can see the significance tests here. So basically saying that direct and keyboard and mouse are the only statistically significant differences within ANOVA, but it's trending anyway in the direction we think, which we expect, which is nice. But also, you know, we see the biggest jump between keyboard and mouse and the hand controllers, and a smaller jump, and in fact, a not statistically significant jump between the hand controllers and having the full VR system. And I think what that's saying is that the perception, the 6 degree of freedom interface is a really big deal. And the perception was less of a big deal in making this happen. I think it's also saying our perception, the way that we're showing the perceptual data of the robot from the robot to the person is not that great. And that we could do a lot better when you go and compare that to direct manipulation where they get to use their eyes. And then the NASA TLX is a workload measurement, so lower is better. And again, we see the same trend where the direct manipulation they thought was the easiest. And keyboard and mouse was hard, was pretty hard. The hand controller was somewhat easier, and the full VR they thought was the easiest. But the same pattern of significance with like these stars mean it was like not significant, but it was like marginal. It was like P.056 or something. It was almost significant, so we put it in there with a star. So this evaluation let us kind of quantitatively assess how well this worked for untrained users who hadn't had much experience with the VR system. We also wanted to get an idea of the potential of the system, kind of like how hard does it let us, how hard tasks does it let us do? So to do that, we defined a kind of benchmark set of challenging tasks for the robot, ranging from like connect 4 pieces inside the game, picking up a ball, spooning some food and feeding it to a person, trying to tie a shoelace on a boot, picking up a pen, sweeping, there's one where you're sweeping the floor. And then what we did is we took our expert users, David and Eric, my PhD students. And I don't know if I said this, but like they literally brought the VR system in, they demanded that we buy it, and they did all this work. And unfortunately, Eric couldn't be here. He's interning at Uber today. I was begging him to come to this talk, but he can't make it. So we had our, what's that?
Can we ask a question from the chat?
Please, go for it.
Somebody asked, what kind of lag duration was experienced during these trials?
Lag?
Yeah.
Yeah, so for the user study, relatively little. We did them all at Brown. So you were like, I think in these studies you were literally next to the robot. You couldn't see the robot because the VR headset was on, but you could hear the robot, you know, as you were moving it. The video showed the operation happening at MIT because we wanted to kind of test the lag, and it was notable. It was maybe a third of a second or half a second, you know, in between getting the frames. We did do, like, we are not sending the point cloud from ROS into Unity. We're sending the JPEG images from the Kinect compressed over the wire, and then we're converting them back to a point cloud on Unity's side remotely. Point clouds are much bigger than JPEG images. So by doing that, and we had to do that. It would have been unusably slow if we had not done that. We got the lag lower, but it was still notable. And that was, you know, 40 miles away, and 2 universities that are probably on the same backbone and stuff. So we definitely think that's a major challenge for scaling this up more. And we're thinking about, we actually just wrote a proposal with Keith Winstein at Stanford, who does networking, and we're thinking about fancier ways of defining the network protocol, especially being able to predict the effects of our actions and then use those predictions to compress the sensor data more on the other end. Our goal is to, like, the real killer goal would be to make it fast over a cellular uplink, over a cell phone connection. More questions? I love questions.
And then if anyone has a question.
Release your inhibitions. It's really hard. If you were in the room, I would be like smiling at you and making eye contact, and I can't do that, but pretend I am.
Yeah, and if you can't, I don't remember if people can mute themselves or unmute themselves, but if you can't, definitely, instead of raising your hand, sometimes it's just easier if you ask it in chat, and then we can stuff. So we actually just got a question. Yeah, or then you can ask first, and then I'll read the chat one after.
Gotcha. Yeah, I'm curious, like, so you mentioned there were 4 different type of thing that you measure, and I'm just curious, like, do you measure the subjective load right after their user did per condition, or do you measure after the user did 4 of them?
I don't remember. So I can go pull the paper and see, but I don't remember if we did it in that order. I do think we did within subjects. So they tried all the interfaces, and we randomized the order, but I don't remember if we had them do the workload survey after each interface or all the way at the end.
Cool. Thank you.
And then I actually have a question to go along with that. So we'll kind of go along with that. So did y'all log the actions of the person throughout, like their orientation at each time step? Because I was thinking, as far as what you were saying of networking and predicting human behavior, I would assume that if you have a bunch of log time synced positions of hands, you would be able to predict better. Did y'all do that at all, or have you planned
no,
on
we
doing
didn't.
That?
We didn't in that study, but that's actually really interesting. Like, you don't need to send all the sensor data you're collecting. You only really need to send the data that the VR headset needs to render what they're looking at now in high resolution, or what they're going to look at soon. Yeah, I really like that. Yeah, we were thinking more about like predicting objects, but like actually predicting where they're looking is probably the biggest thing that you can use to decide what to send over the pipe. Yeah. Very cool.
Thanks.
That's awesome.
And I'm no networking expert, but the one thing that just popped in my mind is in the game world where they started just changing their network protocol for guessing what input someone would put in, and they just end up just guessing that the last thing the person did is probably what they're still doing. And it improves like crazy. But yeah, I'm sure.
Yeah. So one of the things Keith has mentioned to us is the gaming community has thought a lot about this, obviously, for like these big multiplayer games. Yeah.
One more.
So yeah, and in a bit, I'll get to what we're thinking about for the sort of next version of all this. Serena?
One more question from the chat. Somebody asks, have you made any research on effective audio over VR teleoperation?
No, and I am really interested in audio and in haptics also, which I think are related. So like, what the challenge in this is that I think is hard to appreciate until you started to play with one of these systems is that the exact time that you want the best, highest resolution vision data is when you're grabbing the object or about to grab it. And that is the exact time when your hand is in the way of the camera. And you're self-occluding, you're blocking what, you can't see what you're doing. And so I think it would be very interesting to play with both haptic interfaces. So with the standard VR hand controllers, maybe vibrating the controller when you touch something, or something more like those phantoms where you can actually push back, which of course is more like the trade-off with that. Like if you've ever used a Davinci or something or the phantoms, they are like mind-blowing, the haptics, like how much your hands get from feeling the contact, like that I'm going down until I feel that I've made contact. Like it really seems like that signal is very important. And it's really hard to do in the hand controller space. I mean, vibrating does something like that, but it can only go so far. And hearing the contact might be very interesting and very helpful, to go down until I can hear that I've contacted with the table. But no, we haven't experimented with that. I've got an Oculus Quest. I just bought one for my house, and it does. And it was amazing. It was surprising me that it had both a microphone and a speakers. So it would be pretty easy to do that with standard VR gear now. So I love the idea. But none of these do that. Although I suppose actually in these particular tasks, the person was next to the robot, so they could hear with their real ears, what the robot did. And it's not clear how much that helped them. We don't know. Okay.
And then
more questions?
Just real quick, could you move the window?
Yeah, I will when we're done. I was since we're questioning. I wanted to see you. I wanted to see you big. Super.
Yeah, you can ask another. We have someone asking if they can ask another. Yeah, ask another question.
Yeah, go for it.
You can unmute.
I'll unmute them.
I can't find them.
All right, you should be unmuted.
Hi, thanks.
Hey.
I have a question about the point clouds and the communication load. I read your Rust reality paper. I think it's very smart that you send only the IR and RGB separately as image files. But then I have a question about point cloud registration on different cameras, right? For example, the Intel cameras with built-in IMUs. They use IMU information in order to clean up the point cloud. So I wonder, like, have you experimented with different cameras and see whether, you would get a worse quality point cloud?
Not yet, but we're about to. So maybe I'll zip forward a bit and talk about that. So what we just bought like a month ago is an omnidirectional stereo camera. So it sees in like 360 degrees and it's stereo of that. And the idea is to, as my collaborator James Tonkin has this fancy algorithm that basically does view synthesis. So what you get is a much more realistic view of the scene using the data from this camera in 3D. And so as you're moving your head back and forth, you're like seeing, I forgot the graphics word for it, but you see the scenes move and things get occluded in the right way. when you move your head back and forth. And this makes people less sick, and it also gives them more situational awareness of what's going on around the robot. So we're planning to put this camera on it's actually mounted on our mobile manipulator's head right now. But what we're also going to do is mount a camera on the arm of our robot, and we have it connect already on the head as well. So the plan is to do view synthesis from these 3 cameras. And the idea is that the arm camera is going to hopefully help us reduce self-occlusion. So like you can move that camera and hopefully you can get a view, you know, as your other arm is going in and doing stuff. So we are going to be playing with calibration and how good we can get the calibration, and it's going to really matter. I can say with the, here's a shot of the Connect view. I can say one of the coolest things about the VR view was for checking calibrations and evaluating calibrations. So here you can see actually in the scene here, this is where the robot thinks itself is, and this is where it actually is, because you can see it in the point cloud here. So there is calibration error in this image, in this setup. Mostly, I think that error is sort of user error. That is, we were able to get, not in this particular image, in this particular run, we were able to get a good calibration, both intrinsics and extrinsics, where it lined up pretty darn well. And the VR was really cool because you could actually see how well it lined up. Where the IMU, I think, would help is detecting when somebody's knocked the camera and that you need to recalibrate, as probably what happened in this picture here, is that somebody knocked the camera and we have to go wiggle our numbers some more. And then trying to do a Kalman filter deal where you can like knock the camera and then update your calibration. And this is actually a really big concern in industry. So I work at Real Time Robotics, which is a startup company, 1 day a week. We do motion planning for robot manipulators, and we have a product called Rapid Sense where we have 9 Intel RealSense cameras around a work cell to try to see all the voxels in the scene. And the problem is that the calibration both drifts over time. These cameras get hot, so a cold calibration will not be the same as a warm intrinsic calibration. And then in many industrial settings, there's vibration, just because there's these giant things moving around and everything. And that's obviously very bad for calibration. So yeah, a lot of what we're doing though, we just like, you know, tweak the numbers until they're good enough and then just move on so far. But I think for scaling this and making this robust for untrained users, doing IMU calibration is a really important research question. And doing self-calibration, like you should be able to look at your arm and see it's not calibrated and then correct it automatically. Cool.
Cool, thank you. I don't think there's any other questions in the chat. So.
Okay. Well, please feel free to chime in. Okay. So
yep,
I
think that's it for questions in the chat. So you can probably resume wherever you feel like it's good to resume.
Yeah, I'll resume. But again, if anybody wants to drop in a question, please go for it. Okay. So we evaluated the system in one way by having untrained users come in, do one defined task, and then quantitatively and qualitatively evaluated what they thought of it and how long it took them to do it. The other way we wanted to evaluate the system was by pushing the limits of the whole thing. So we defined a set of ambitious tasks and tried to see for each of these tasks, and we made them up. You know, we were trying to get a diverse set of challenging tasks to do different stuff that it seemed like it might be useful for a robot to do. And then for each of these tasks, we tried to do it with direct manipulation, where you put your hand on the robot arm and you try to move the robot. And then we tried to do it with VR, with an expert operator. And the yes means that an expert operator, after trying and playing around and maybe failing, eventually they got the task to work. They could do it with VR. And in no means it couldn't. And we tried direct manipulation first. So if they couldn't do it with direct manipulation, we didn't even try it in VR, because if you can't do it with direct manipulation, there's no hope. And what we found, I actually feel like, in a way we define these tasks, like I really want more that flip. So like block stacking, where you could do it in direct manipulation and you couldn't in VR. But we had relatively few that we could do in direct manipulation and not in VR, partly because I think we were really, peeling a potato, they could in direct, but not in VR. But partly, as we were defining, like we were the ones defining these tasks, and I think we were motivated to make them work, to pick ones that worked. And despite that being the case, like the sort of flawed methodology, I still think this has value, both in like putting out a benchmark set of tasks, and I think there's a lot of value in kind of thinking through what such a benchmark would look like and defining one. I mean, that might be something for this workshop to think about. What is a set of benchmark tasks for a manipulator or for a mobile manipulator that you would like the robot to do in both teleop and in autonomous and in direct manipulation and in all these other modes.
Can I ask a question? Sorry.
Yeah, please.
How come block stacking failed in VR when so many like more complicated seeming tasks worked out? Do you know?
I actually don't know. I was like looking, I think it's probably because the blocks, as you can see here, are pretty small. And they're supposed to stack the tower pretty high. And if you have to do a lot of pretty accurate places, basically, to do it, is my guess. And I suspect that comes back to the perception stack not being very good. You can't see exactly where that block is. Okay, and here's the example of that. And this is also an example of like, so you can see the person is next to the robot using the VR system to fold a shirt. Okay, so my feeling is that the major limitation of this system is the perception stack. Both the fact that we're rendering this as a point cloud instead of doing the sort of low-hanging mesh reconstruction, but then also the fact that our camera has a limited field of view and a relatively low resolution for what we're trying to do. And I think you could do a lot better if you had better sensors and more sensors in more places. And that's what we're doing in the next iteration of our system. So COVID isn't stopping us. We put the camera on the robot, and we're trying to do with this omnidirectional stereo, and as I said, 2 cameras, trying to reproduce that PR1 video, which I sort of see as a key benchmark in this space. Is why doesn't that video exist? Like, why doesn't everybody? I think everybody with mobile manipulator robot should have equipment now to produce that video. And I think VR is actually a key enabler for that. Like the existence of today, consumer VR, right? At the time that video was made, that was like before the Vive, right? And before the HoloLens, and before, I could buy for less than $1,000 an Oculus Quest that doesn't even need lighthouses, and I can play VR games in my living room. I think this is a tremendous opportunity for robot teleoperation, and I'm hoping that we can create a new wave of teleop and then all of the ancillary benefits of that, both in helping autonomous robots recover from failure, but also providing training data for our autonomous algorithms. Okay. All right, and it's almost an hour. So I will skip augmented reality. We did also play with the HoloLens, and we did some augmented reality stuff. But I'll skip it. There was a paper about it where we showed the person in augmented reality. I'll show you the video. We showed them the trajectory that the robot was going to do in the future in AR overlaid over the real world. So this is kind of showing what it looks like if you were wearing the HoloLens. As you're moving your head around, you see this ghost robot, and you're seeing different trajectories that it's going to take. And your goal is to see if this trajectory that it's proposing is a safe trajectory or not. Is it going to collide with these cardboard thingies? And we compared this interface with a 2D interface and with no interface, where you just had to hit the stop button. So here's the 2D interface where you kind of see it on a screen, and then the no interface is just the arm starts to go and you got to hit the stop button before it happens. And we showed that augmented reality is good. It helps people more accurately do this task of detecting the movement. So monitor, no visualization, you just hit the stop button, and then there were numbers and users and stuff. We've also, my main line, most of my work is language and robotics. But we've also done a couple, like what I've been excited to see happen is our work in AR and VR has kind of moved from, it's sort of percolated into our language papers, where it's allowed us to create and perform tasks that are too hard for us to make the robot do in real life, but that we can actually make a really convincing and interesting version of it by using augmented reality. So here in this case, the idea was combining language and mixed reality. So you could say stuff like, take a photo of the green box. And the challenge is if you use a landmark like the green box or the blue chair, is in real life, the robot might not know where the blue chair is. It might have never come into its field of view. If it did come into its field of view, it might have never run the detector. It's really hard to map the words blue chair to a thing that the robot can do. But with augmented reality, we can actually define our own landmarks, and by calibrating the robot to the mixed reality headset, we can then use those landmarks and know exactly where they are. So the idea was that the person could use language to refer to landmarks like the green box that only existed in mixed reality, and that the user could create and put exactly where they wanted, and kind of combine the robot and the language interface with a mixed reality interface. That was at ICRA a couple years ago. And then in this paper, I won't go into the details of it, but we defined a very rich natural language a task environment where the drone was flying in a 2-story building. And it would be very expensive for us to actually get a 2-story building, evacuate it so that there's no people around, and then make our drone actually fly in the real 2-story building. But for me, it's always been very important to have the real robot demo. And what we did is we had an augmented reality simulated 2-story building with a real robot flying around inside of it. So we were able to demonstrate that we could do the task in this kind of virtual augmented 2-story building. And I told my students I was excited that augmented reality was like not a focus. It was just like, oh yeah, we're going to use augmented reality in this paper because it makes sense and it's the easiest thing to do. It was really becoming like a tool that in our toolbox that we bring out when we need it. I'll skip the video. I'll skip that. So my lab is also doing a lot of outreach, and the VR in particular has been a wonderful tool for our outreach. So we have done, we've either brought it into schools. I brought it into a school here in Cambridge. I live in Cambridge. I work at Providence, but I live in Cambridge. We brought it to Cambridge Regional Latin High School and loaned it to them for 2 weeks and let them play with the headset. I brought it to an elementary school in Cambridge. This is a shot from that, where we let them play with Google Earth. We loaned it out to our high school in Providence, the PCTA, and they took it to their middle schools. So they took it to their feeder middle schools and let all of their feeder middle schools play with the VR system. It's a super exciting technology that kids they just love. And so it's been a really exciting way to get people excited about robotics and about STEM and about graphics. All right, and I'll finish there. So I talked about virtual reality for manipulation, augmented reality for motion intent, AR and VR for increasing the complexity for robotic tasks, and our lab's personal goal, which is to reproduce that PR1 video. So if you may or may not have noticed that the title we don't actually deliver on. We are not teleoperating mobile manipulators in VR yet. But I titled it that way because that's what I really, really want to do. I think that the PR1 video is kind of this stake in the ground. And if that could be reproduced and then spread widely through the community, I think that it would be a great advance for robotics and all parts of robotics. Thank you. Yay.
Thanks so much, Stephanie.
Yeah.
Yeah, that was great. We will have about 30 minutes here for discussion. So if you have any questions, actually probably the best place to ask them or right over the chat. And just to kind of get us started off, Adam posted something about the idea of tasks and benchmark tasks, which is always kind of a controversial topic, I think. And how, in terms of benchmarks for directly moving the manipulators in VR, there's some work at NIST where they've created standard task boards to assess how well collaborative robots can do assembly tasks. Mm-hmm. Do you have any thoughts on that, or?
I don't know much about that task, but one of the things to know is that the term, wow, that's interesting. We should definitely check this out. Can I just look at it now? Can we see the task boards? Yeah. Cool. Can you see my screen, or I'm looking at that?
I believe you're just sharing your PowerPoint.
Gotcha. Let's see, if I stop share and then I share my web browser. All right, here it is. Yeah, this looks really cool. Oh, CAD models and STL models, this is great. And then in the competition. Very cool, and this has got like stringy things and wiry things. So yeah, so collaborative robots is a code for robots that promise if they hit you, they won't hit you too hard. But they still might hit you. And a lot of their use cases are industrial use cases. So what I would also like to see in a set of benchmarks is like home kinds of use cases. So like cooking sorts of tasks, cloth and laundry folding. And then clutter, manipulation and clutter, where you've got lots of stuff around that you have to deal with to pick up the thing that you're trying to pick up. But maybe it makes sense to have like different domains. So like there's the home domain, and then there's the industrial domain, which this looks like it's covering. And then, you know, I don't know what else.
Yeah, I just realized I could unmute myself. Yeah, I realized this is more for like industrial and assembly use, but it could be of interest.
Yeah, this is great. And there's nothing wrong with, by that, I don't think there's anything wrong. I think we want industrial and assembly use. So I think but I think we just want more than just that. So this is cool. We should use this, and we should add to it, you know? So what is your vision on VR-based control for mobile robot and a mounted manipulator? Yeah, we did a prototype of that with the PR2. And what I think should happen is we should take the SLAM map that most robots can produce, and then make that, like, lay that out on the ground in the virtual world, and then use the sort of, it seems like the VR world has these standard teleporting things, right? To teleport you around inside of virtual worlds, and basically create an interface like that where you can point with the hand controller and teleport around the 2D map. And then I think what you should do is be able to set waypoints on the ground in the 2D map. So like an X, Y, theta for a mobile manipulator to drive, and then it can make plans to drive to those waypoints. And then I think you should be able to like have some kind of, we were talking about like graying out old stuff, but like basically as your robot, as our stereo 360 camera is driving through the environment, you're going to be able to collect logs of the environment that you're moving through, and and then, you know, if you were somewhere 5 minutes ago, it would be nice if you could see at least what was there 5 minutes ago when you were there, you know, in the 360 view, but maybe it's grayed out or something to indicate it's not live. We haven't built it yet, but we've been thinking about concepts for somehow showing the person, this is old sensor data, we're going to show it to you so you have context, but we haven't updated it for more than a minute and we don't know if it's still like this.
It's funny you mentioned the teleporting. One of the papers this morning was about that, I believe.
Oh, that's great.
Yeah.
Awesome.
So if anyone's interested in that, it's one of the papers. I'm forgetting which paper number, but I can put that in the chat too.
Super, super. Yeah, I think that's awesome. For AR system, how do we register the headset to the robot in order to accurately overlay the world? Hacks. We have a hack. So basically, we have this calibration step that's manual, where we drag the robot, you put on the headset, and you drag the virtual robot model so that it overlays with the real robot. We tried playing with like AR tag kind of systems where you had, what do you call those little fiducials? Fiducials is the word. But it turned out to just be a pain, and it was easier to just drag the robot over stuff.
Yeah,
calibration is a big deal. It's like one of those things that's like brushing your teeth that like nobody talks about, but if you don't have a good calibration, everything sucks.
Yeah, that's something I'm also super interested in. I think a lot of people in the community are interested in how do we calibrate to the robot. I think everyone had the problem. I had to get arms on a robot, and I actually took the cursor and told the participants to put the cursor on the robot, put the spatial mesh, and told them to put it at an exact point, and then I spawned on the whole world around it. So there's another little hack where you don't need to drag it, but also not necessarily the best way. But yeah, you can take on whatever the next question was.
Yep. Okay. So yeah, and Dan Schaefer's lab, as Thomas put in chat, and I should have mentioned this, has done some really cool work. We were on the same NASA like early career award class or something. So I got to hear a lot about his work at the same time we were doing our work. And it's having robot drones kind of show what they're about to do, and exploring different interfaces to say what's happening with the drone. It's quite cool stuff. Okay, so Tom, hi Tom. So as a language learner whose lab is also working on robot communication via AR and language, how am I thinking of using these new directions in my language-centered work? Yeah, so I talked a little bit about that at the end. It's letting us scale up the complexity of our tasks. So we're able to define more complicated tasks in virtual environment than we could do if we had to make that in a real environment. And we did that landmark paper where we used augmented reality as a way of creating landmarks.
I guess I'm curious whether you have plans for...
Oh, you're very quiet.
Really?
I don't know if that's just me.
That's
better.
I guess I'm curious whether you have plans to, not just in the using AR as a tool within the context of the robotics experiment, language-centered robotics work, but also in terms of the AR as communication channel, because both are super interesting.
Yeah, we have a paper we never got published where we tried using, it was based around our social feedback work, where we were having the user try to get the robot to pick out an object. And if the robot was confused about so you'd say like, get me the big red marker, and you'd point, and the robot would try to figure it out. And if it was confused in the original work, we would ask a question. It was all language. But my students like really believed in the AR, and they were like, no, this should be AR. Like if you're, and they made an AR interface where the robot could indicate with like colored highlights around the object how how likely it thought it was. And then they actually ran the largest user study I've ever run in my lab. I was like, we're really doing this? Like, it had like 100 subjects. Like, it was kind of crazy. And then it got rejected after that. So we did do a dive in that direction. But we haven't done much since that time. David Whitney was the student of mine who was really spearheading that cross. He was doing both the social feedback work and the AR. And he is now at Uber, or Facebook. Facebook, sorry, he's at Facebook. He graduated. So we've done less at that intersection since that time. And our new thrust is really going back to VR and trying to increase the perception. To do, I don't know what will happen after that. We'll probably do some language, because we always do some language. But I tend to be very opportunistic in my research, and I find with these interfaces, there's really nothing that can replace like putting on the headset and playing with it and trying it out and seeing what it makes you think of. So I don't really know what's going to end up happening, but you know, I can tell you we're going to put the headset. One of the reasons I bought a VR for my house was partly I wanted to play. Have you ever played that Jedi? It's called Vader Immortal. It's like so good. Really good game.
It looks great.
It's amazing. I love it. You feel like a Jedi. The lightsaber dojo, it's like my physical exercise now is like being a Jedi. So I won't deny that was motivation. But also I wanted to be able to try out the interfaces, and with it being hard for me to get to my lab, I felt like I needed to have something in my house so I could do that. You know, I really think, you know, a frontier is putting something. I was telling them, I know I'm confused about the ecosystem of it, but like putting something in the Oculus store and in the Steam store where they download our code and then they start teleoperating our real robot and participating in our user studies, I think would be amazing. You know, an amazing way to get subjects. It would be totally quarantine friendly. And I think people would love, you know, participating and playing with the robots and stuff. And it'd be a really cool form of outreach as well. So I've been trying to convince them to do that, my students to do that. I don't know if you have to convince your students. I find I spend a lot of time trying to convince them, but usually when I fail, they're right and I'm wrong. So it's all good. In the 360 video-based teleop, where would the operator be? Yeah, no, I definitely think, so where would the operator be? Would the operator share the head with the robot? Is there a way to decouple the operator and the robot in the 360 video? I think a huge mistake in early robot teleop interfaces was to tie the VR headset to the camera and make the camera follow you. And a huge opportunity in this space is that the VR headset lets you decouple your head from where the camera happens to be right now. So we definitely want the operator to be able to move around, although that's going to look weirder. Like as you get farther from where the camera actually is, you're going to have more weirder artifacts. But it's going to be possible. And the other thing we were thinking, and we haven't really made interfaces for this yet, but like, you know, I imagined that you would be like, a key interface concept is that I can't have cameras everywhere. If I could, I would. You know, if I could, I would stick a camera like on a drone or something and fly the drone wherever the headset is right now, so that I could get the data from exactly where my eyes are looking. But that's impossible. So I think that there's a real interface challenge to like exposing that complexity of like, where are the cameras right now, especially if I have one on my arm that I have a lot of choice over where it could be, and where can I move it to so that I, the operator, can see what I need to see to do the task. So I'm really optimistic about the camera on the arm, because I think that can really avoid, like you can have the manipulator arm coming from the top and the view from the side. So it's not occluded as you're going in. And I'm hopeful that will provide a perception interface better than anything we've been able to create so far.
If I may, I have two follow-up questions. First one regarding 360 videos. As far as I understand, 360 videos are like a video that is mapped on a sphere, isn't it?
Yes.
Wouldn't that mean that, like in the virtual reality, you have a sphere around robot that runs the video, but as you move within the sphere, your perception of whatever the image on the sphere is like is going to be distorted. Is that
so we're doing, and I'm not doing the magic. James is doing the magic, but we're doing deep learning magic to construct a 3D model of the scene, so that as you're, do you guys remember the name of it? James said he might come, and then he could tell me the name. There's the name. I forget the name of the thing. Parallax? I think it's parallax.
Parallax.
Yes, parallax. Good, thank you. Okay, so it's gonna reproduce parallax because it's stereo 360, right? So you're gonna be able to get you know, the 3D structure, and so then as you move your head back and forth, the thing behind is gonna move, or the front. I'm not doing it right with my hands, but like as you move your head back and forth, and there's something closer and something farther, it's going to do the right thing with parallax. And that will look better if you're near the center of the camera, and worse if you're farther away, because you're going to lack data, you know, to reconstruct everything. Does that make sense? But I think that general thing is a huge research question. You know, how can you make that look as good as you can, as far away from the camera as you can? Sorry to interrupt, go.
Actually, two more. You were talking about the camera on the arm. Do you mean also a 360 camera?
I wish, but no, it's gonna, the 360 camera is like really expensive. So I was surprised how expensive it was. It's like 8K or something. It's really expensive. So unfortunately, I cannot sprinkle them everywhere, which is kind of what I want to do. So we were going to use a Kinect or a RealSense depth camera instead.
I see. So you want to watch with one arm what the other arm does.
Exactly.
Are you aware of the? There was this paper by Daniel Rakita from Madison about teleoperation, where he had one robot operating and the other robot autonomously following and watching it.
Oh, cool. No, I'm not. I would love to know about that paper.
And that made me think about directing the secondary camera based on whatever operator looks in VR. So say operator looks at the, I don't know, at the object, in the direction of the object. So to make the secondary camera to follow the gaze. Do you think that would be a viable control interface? The
challenge, oh, Bill Gay, awesome. Bill Gay's great. I'm gonna write that down. I'm gonna stop screen sharing while I do that. Okay. The thing about that is that the robot is always going to move much, much slower than the person. About robot following another robot with cameras. I'm just writing down the Bill Gates note. The robot is always going to move much, much slower than the person can move. And you want that to be the case. That is, it is scary to have the robot move as fast as a person moves. It's dangerous. So we don't like, it's a fundamental fact that the robot will never be able to move as fast as a person. So the challenge with moving the camera around is that you've got to be tricky about how you keep things up to date with where the person's looking. That might mean doing something like a moving average or a predictive system where you like try to predict where they're going to go next. And I don't know, like I think that it's a really interesting research question, but I definitely think the naive thing of just trying to follow their gaze is it's gonna be really slow.
I see. Thank you.
Yeah, and another paper shout out from this morning is also another where they were dealing with occlusion and using, I think it was called Octomap or something, where you just have a permanence of you basically take a depth image of an object and then you keep that permanent while you're moving the camera closer as like a fake real object. That makes sense. I think that was paper 2. But yeah.
Cool. I'm writing these down.
Other questions? Great questions so far.
Yeah.
Oh, I do have a question now. So 10 minutes ago, you mentioned that you did a project in which the robot asked to clarify the target object. So I'm just curious, like, what kind of considerations or factor that you use to build your active learning model so that the robot knows what question to ask? Like, I imagine like there must be some sort of like which task it's doing, where the object is.
Yeah, so we had a POMDP dialogue model. So we assumed that we knew the task and that the task was object fetching. And furthermore, we assumed that we knew the space of all the objects that the robot could fetch and that space was complete. So then we had a belief space over what object the person wanted, and that was a multinomial, right? So we're trying to estimate which object we think you want, and then we have a multinomial distribution over that. So then you can frame it as a state estimation problem where you get to observe their language and their gestures. So pointing gestures, and you can write down the probability of an observation given the true state. So we had an observation model that was like, you're likely to point at the object you want. And we had a language model that was based on keywords, although in reality you would want to learn it, but we just wrote down some words. Like if it was a marker, then the words were like marker, pen, red, stuff like that. And then that let us fuse information from language and gesture and do the POMDP belief update. And then the POMDP's policy was based on a reward for handing over the right object, a cost for asking questions because it bothers the person, and a big cost for handing over the wrong object. And then depending on those thresholds, it decides, and you can tune those, and of course, what should those rewards be? We picked some magic numbers that made it do more or less the right thing, but like, you know, we kind of wanted it to avoid asking questions if it was like more or less sure, but if it isn't sure, it should ask a question, and we tuned the numbers until that's what happened. And then we had an autonomous system that, you know, where we had people come in and we didn't tell them how it worked. And it was quite cool, actually. Like, despite this, what I liked about that paper was that the system is actually quite simple. Like, there's no deep learning. It's just a multinomial. It's a manually specified language model. There's no spatial language at all. And yet, the language and the gesture fusion happened so quickly and so intuitively that it's actually very effective at quickly handing over the right object. And a lot of our users, like almost half our users, thought we could do spatial language, like to the left of, when we can't. We just totally said no spatial language, done. But because the language and the gesture fusion was so natural that they thought that it could when it couldn't.
Gotcha.
But that published paper had no augmented reality. It's an unpublished paper that is, you know, I forget if it's under review right now. I forget where its status is. We've been resubmitting it and trying to get it out, but, you know, reviewers are reviewers.
Gotcha. And then you briefly mentioned deep learning, and I'm just curious, like, what is your thought on GPT-3, since it's pretty hype in the deep learning world at the moment?
Yeah, and I think there's, I mean, you know, people call it hyperparametric function approximation. If you take a lot of data and crunch it for a long time, then GPT-3 is what you get, and I'm glad someone's trying it. I was kind of upset when they, I don't know if you know that some of my students reproduced GPT-2 after they stopped. They said, we're not releasing GPT-2 because we're afraid it's going to take over the world or something. And my students were like, no, this is wrong. Like, this is just a language model. Okay, so I'm sorry, my phone is ringing and I'm giving another talk today, which I believe is at 3:45, but the organizer is calling me. So I'm hoping it's not now. But I guess, I'm pretty sure it's not now. So I'm going to not answer his call and call him after this is over. Sorry about that. It's actually about the Hilbert questions of AI. It's a panel. I'm really excited about it because I think that we need like Hilbert questions related to GPT-3 actually. I think that GPT-3, you know, is showing that, you know, that humans are really smart and humans can write lots of really cool things, and the statistics of that, if you have enough data, can actually capture quite a lot, and that's pretty neat. But I think that's a long way from having an autonomous, intelligent agent with sensing and acting, making decisions in the world. Me and George and Michael at Brown, like, we really believe AI is a robot, and you know, I think that they're nearing a ceiling, actually, in terms of what these models are going to be able to do. And it's natural we would approach that ceiling, and I think that it's doing sort of what you would expect for the ceiling. Yeah.
Thank you.
The next question is selfishly for me. For outreach regarding AR, VR plus the robot, how do you think you could accomplish this given COVID? I'm particularly interested in education myself. I work with robot tutors and AR, teaching coding. So like, I'm particularly interested in any ideas you have for outreach.
Yeah, I think that VR itself, as it becomes a consumer technology, is an exciting vector for outreach. On the other hand, I think that there's an access issue with that. That is, it's still pretty expensive, and you have to own the headset in order to use it. But a lot of people do own those headsets, so I think it's silly to not take advantage of that opportunity. I also think, you know, we're doing this drone project where we're giving out drones. We're giving out robots to people. And I think, you know, I've always felt that you have, like, for robotics in particular, you've got to have a physical piece of hardware. And for outreach, we thought a lot about what it needed to have. Like, we did not want people to install ROS, and did not want ROS to be a requirement. Eventually, you're going to have to install ROS if you get in. If you get on the train, ROS installation is in your future. Installing Unity is in your future, right? But to get on the train, I think you should not have to install those things. And one of the advantages of our framework of giving them a robot is we're giving them a Pi, a Raspberry Pi. And we are giving them a disk image with everything installed correctly. And then the idea is that to get on the train, all you need is a web browser. And we will give you SSH access, we will give you shell access, we will give you control access for the drone through your web browser, and then we will be able to scaffold you step by step so that you can learn the command line, you can learn stuff that, you know, a lot of us just know now, but like, I don't know how we learned it. Like, so the goal, I think one of the challenges is to kind of broaden the pipe and to make that on-ramp as large as we can, and to have as many diverse on-ramps as we can as well. So one of the questions I get asked about the drone project is, you know, why drones? Like, it makes so much more sense to give people ground robots. You know, God help us, we're giving them a flying projectile and putting, you know, wings on it and making it go up in the sky. It's terrifying. But one of the results in education research is that, you know, students are diverse. Students have different interests. Students may come to robotics and to virtual reality in many different pathways. And so it's incumbent on us to offer, you know, many different pathways into robotics. We need the drones, and we need the ground robots, and we need the underwater robots, and we need the virtual reality pathway. We need all of those pathways to bring people on board. And I you know, I think that's an important thing to think about.
Cool, thank you.
Yeah, Unity itself is actually quite good. My son is son. Can I brag? I have a 7-year-old son, and he's learning Unity and C#. And so we've been watching these like crazy videos of like really cool gamers. Do you know Danny? I don't know if you've ever seen this guy, Danny, who's like this young kid who's producing these Unity tutorials and stuff. And I think that's great. Like, you know, showing people how to install Unity, how to make a collision detection, how to do rigid bodies. But, you know, he's like trying to figure this out. And of course he has me to help him. And I don't think I mean, I don't want to give myself too much credit, but 7-year-olds and C# weird compile errors are not, you know, not good. So I think there's still a lot of barriers along the way to, you know, getting people making games instead of just consuming games and stuff. I love games. I think games are underappreciated.
Oh, I'm on the same exact train. That's where a lot of my stuff for robotics, I just say, oh, they did it in games, so probably works.
Yeah.
And that's also what I tell people in outreach. It's like, if you want to get into robotics, if you learn some game stuff, a lot of it translates really well.
Yeah.
To steal the next question from Michael, he was asking about how do you develop for the HoloLens, for AR, VR. What I would say for this question, and we'll probably go to the next question, is go to the software programs channel on the Slack. We've put in a bunch of stuff for development. And how do you get, well, like what packages do people use that are open source for development? To answer your specific question, there already is there's a ROS Bridge package called ROS Sharp. It actually came out of, well, a branch of it for HoloLens came out of Stefanie's lab from David. So definitely go check that out. So I guess we can probably go to the next question in the chat, which is in regards to the camera arm concept. Do you think this could be a region where robots with more than 2 arms have potential? For example, a robot with a 3rd camera arm that can intermediately reposition in VR, but most of the time the user maintains extra 2-hand control of the robot.
I suspect yes, but I assign a large uncertainty to that yes, because I've never really seen, like you saw in our videos, like we had a wrist camera actually, but the view of that camera should have been projected onto the point cloud, but we never did that. We just had it floating in space, you know, next to the arm. I would love to see an interface where you were fusing multiple cameras and projecting it onto the mesh of the 3D world. You know, we're working on trying to make that at Brown, and I suspect that once we see what that interface looks like with 2, we'll have a sense of whether more will matter. But I guess that it will, because our eyes saccade so fast and have such high resolution at the fovea that I suspect is the more cameras we can have, the happier the person's going to be, and that's going to push the envelope in terms of the dexterity of the tasks the robot can do. Our robots can move at microns, right? Like they can position themselves at, you know, at 6 microns or something. Like our, you know, modern industrial robot, they are very precise. And that means if we can get the perception there, they can do things very precisely. But I think that says we need lots of pixels. You know, and we need them where the arm is doing the deed, but we may also need it around in the scene. As you get more arms, I think there's a control question too. So like, you may want more autonomy in terms of where you're pointing those cameras. Yeah.
Cool. I guess we can go to the next question, and then Tom said, as a side note, you might also be interested in a panel discussion fireside chat with Gary Marcus and Ken Forbes talking about the future of AI. That's 5:30 Eastern. And then next thing is, could we hijack Unity as a potential front-end simulation engine for ROS to bypass the current ROS Sharp method of having to have ROS running in an Ubuntu VM? Has anyone tried this?
Maybe. You'd have to do a lot of work to recreate the stuff ROS is doing, which is primarily integrating with a lot of different sensors and actuators. None of that work would be technically hard, conceptually difficult. It would just be a lot of slogging to hook up all of those pieces and make the plumbing work. And the thing about ROS is that it sucks. It does suck, but it is currently the standard in the community. Every research robot that is produced today has a ROS interface that comes with it. And that is a big part of why we did it the way we did it, is because we didn't want to take on trying to reproduce all of that in Unity, which is sort of what you have to do. I think that ROS sucks, and unfortunately the ROS developers, the Open Source Robotics Foundation, they're making ROS 2, and I think it also has a lot of serious design flaws. I do see a role for something like Unity or some other thing to kind of replace it, but I it's hard for any research group to play that role. ROS itself was created as part of Willow Garage. So they were funded by Scott Hassan, who had made a lot of money from Google, to employ, I think it was 30 or 40 full-time engineers until Scott got bored, which is what happened. Eventually he said, we're done. And that was the context in which ROS was created. It was that we're making the PR2, we need a middleware stack, we need to standardize on something, and they made ROS. And because they put all of that, person hours into it, testing it, creating it, making it run on many different robots, that is what gave it the momentum that eventually, like the inflection point was that Baxter, for example, supports ROS, and Baxter, was made by Rethink Robotics, and they aren't part of OSRF, but they understood that Willow spun out OSRF later to sort of push ROS forward, and OSRF still exists. And so, companies like Rethink knew that they had to support ROS on their research robot platform if people were going to use it. And so that's where the world is today. And that's what would stand in between you and using Unity in that way. It's definitely a more elegant design, though, I agree.
Cool, thanks. Yeah, if anyone wants to do that, you make it, I'll use it.
And we'll use it, right?
Yeah.
Yeah.
Are there any other questions from anyone?
I do have another question. So I'm just curious, we still don't see a lot of home robot, and recently, last year, lots of home social robot got shut down. And I'm just curious, what do you think is lacking in this type of robot that we don't still have one that is common in the house yet?
Yeah, we do have the Roomba. That
oh
worked.
Yeah, the Roomba. Yeah.
So don't forget that.
That one.
I think that the home killer app is something like pick and place, generalized pick and place, where I can say, bring me this and bring me that, and it actually can do it. In order to do that, I think that a wheeled robot is not going to do it, because homes have stairs, and any robot that is limited to one floor, I think it just cuts out so many of the use cases that as a commercial product, it doesn't have a chance. So the Spot Mini was extremely exciting to me because I was finally looking at hardware that I thought could do it. But the software side is equally important. As you know, the PR1 was teleopt, right? If you look at Covariance, that's Peter Beal's company, that's doing mobile manipulation in an industrial setting. With robots, with a non-mobile manipulator robot, and that company is a big deal in part because it's able to very robustly plan suction grasps for diverse objects. That is still, and that's that's a big deal. That's a huge advance for industrial robotic pick and place. That is still way easier than what you find in the home with clutter and messes and all of that. Yeah. The other challenge with the home is the economics of the home. So a factory is willing to pay you a lot more money for your thing than any consumer will. So the price point of your robot with all of its sensors and all of its software, inherently, the home works because it's a really cheap thing that gets sold to a really large number of people. And we are frankly nowhere near that yet. No one is going to pay $10,000 even for a robot in their home. Probably. So, whereas in the industrial setting, yeah, they're going to pay that. They're going to pay $50,000 because it's going to run on the assembly line and it's going to make it back. So what I expect to happen for manipulators in the home is that the industrial stuff is going to crunch. Because they have the capital to make these investments and to bring stuff like covariance, stuff like real time to market, and that's going to produce a base set of technologies like the real-time motion planner, like Covariance, Vicarious, they're both doing the same thing. Yeah, Covariance is the one I was talking about. Like Vicarious is pick and place. They're going to bring the cost down of that. And then we're going to see plays for manipulator robots in the home. But I don't think it's still a ways away because of those reasons. There was just a new robot announced at RSS from Charlie Kemp and a few others that is a lower degree of freedom robot arm. So it doesn't have the full 7 degrees of freedom. It has a fewer number of degrees of freedom. And I think the price point is more like $1,000, which is sort of in the ballpark for a person in your house could buy it. But it's still wheeled, which as I said, I think that is going to cut out a lot of the use cases. So I don't know. I think that's sort of where I think it is. And then in the Jibo land, you know, with these social robots, Jibo, I think Jibo had a shot, but Alexa came along and smoked them. And you know, it could be that the extra complexity of the robot was too much. And that's maybe one reason why Alexa smoked them, was they realized the essential thing of this thing in your house was just the talking and the information and not the social robot. And I don't know if you've seen Jibo. Like, have you seen one? Like, they're weird. Like, I think they're a little creepy. I think they're a little bit in the uncanny valley. They're a little annoying. They interrupt you. Like, you know, and you know, George got one and was saying, like, I don't want to invest, like, I have a limited amount of energy for social interaction and I don't want to spend it on my robot. I want to save it for like people. So it was, you know, I think they got some things wrong on the design, I guess is how I put it. But you know, somebody, it was, I forgot his name now. He's from, he was, oh, what's that?
Talking about Guy Hoffman's robot?
No, it was robot? This guy from USC, from Ross Mead. Yeah. Yeah, he was telling me that the fact that Jibo existed and got funding and got traction says that there's a there, you know, that there's a social robot oasis out in the desert. There's a use case for it, and what's happened is that people have, you know, struck out on their caravans and run out of water before they got to the oasis. But but maybe somebody will figure it out and get it right. I don't know.
Yeah, thanks. Ross is from the lab that I'm in, Manipulators.
Yeah, Manipulators.
Assistive robotics.
Yeah, I was gonna say, I bet you know his name, but then I remember.
Yes. Oh yeah, I know Ross. Yeah, he's great. Just as another shameless plug for our work. If anyone's interested in talking about socially assistive robotics, you can ping me on Slack. I have lots of opinions. We're hitting right on mark here. It's 11:40 my time, which I think is 2:40 their time.